A proportional odds regression model is a preferred way to model the responses of an ordered multi-category response variable, primarily because we only have one parameter representing each explanatory variable in the model. So for example, we had a beta 1 times x1, a beta 2 times x2. But you may be wondering, well, what if we did allow to have more regression parameters in the model corresponding to a variable, such as this model here? So all I did was take my proportional odds regression model and plug in a J subscript with the corresponding subscript that we had previously for the regression parameter. This kind of model is called a non-proportional odds regression model because now we no longer have those proportional odds that we saw before, meaning that the odds and then the corresponding odds ratios for each explanatory variable will change as a function of J, our response for Y. Now, with a model like this, what we can do is actually do a test for the proportional odds assumption for a proportional odds regression model. So the null hypothesis model will be the proportional odds regression model. The alternative would be the non-proportional odds regression model instead. And so this is what then the corresponding parameters would look like, or hypotheses would look like. Let's say that I'm only interested in testing the proportional odds regression assumption corresponding to explanatory variable R. So you could actually have a mix in your model of whether or not, let's say that J subscript is on some of the betas or maybe not on other betas. And so we can test the proportional odds regression model for that corresponding explanatory variable with this set of hypotheses. This leads then into a nice form of a likelihood ratio test. Now, if the proportional odds assumption then is rejected, well, it may be preferred to use the non-proportional odds regression model for the data of interest because we reject it. However, we run into the same problems that you've seen hopefully previously in an introductory stat course regarding doing hypothesis tests when you have, let's say, equality in that null hypothesis. Basically, just to review, if you take a large enough sample size, you are at some point still going to end up rejecting HO, even if that null hypothesis is only violated just by a little bit. And that's a problem with any kind of hypothesis test whenever you have equality in the null hypothesis. So that is one problem. Here's a bigger problem though. The non-proportional odds regression model allows for the following. The probability that Y is less than or equal to J can be less than the probability Y is less than or equal to J prime for J greater than J prime. To put some numbers with this, what this means, for example, you could have something like this. The probability Y is less than or equal to 3 could be less than the probability that Y is less than or equal to 2. That can't happen. Because remember, these are cumulative probabilities. So this probability here should include all of that probability plus the probability Y is equal to 3. But unfortunately, the non-proportional odds regression model allows that to happen. Here's an example. Earlier, when we first looked at a proportional odds regression model, I did a plot of what that model will look like. Let's do exactly the same kind of plot now with a non-proportional odds regression model, where I'm going to use exactly the same beta 1, 0, beta 2, 0, beta 3, 0 that we've seen before, so the intercept term. Now previously, when we just had beta 1 only, we use beta 1 equal to 2. But now since I have the subscript J on the beta, I can have a beta 1, 1 equal to 2, a beta 2, 1 equal to 3, beta 3, 1 equal to 6. What does this model now look like if I were to plot it? Here we go. So on the left side, we have these cumulative probabilities. On the on the x-axis have values of our explanatory variable. Now the part that causes a problem with this model is right down here. Probability that y is less than or equal to 1 can be greater than the probability that y is less than or equal to 3. That can happen. We have these cumulative probabilities. And it's only even more dramatic when we look at the plot on the right side. I have pi sub j here on the y-axis. Again, values of x sub 1 on the x-axis. Look what happens here. For pi sub 3, it actually becomes negative and goes off the plot. Can't have negative probabilities. So that is a problem with using a non-proportional odds regression model. Now, if you wanted to use the likelihood ratio test to test for the proportional odds assumption, unfortunately, you cannot estimate a non-proportional odds regression model with PLR function. Rather, you do have to go to the VGLM function. If you want to see how it's done, please take a look at my book where I actually show it. Now, there are other kinds of regression models for multi-category responses. In chapter 3 here, I focus on the two most prevalently used models. But another model that could be used could be formed like this. This is called an adjacent categories model, where I have the log of pi sub j plus 1 divided by pi sub j on the left side. Notice how category j and category j plus 1 of y are adjacent categories. So that's where this name comes from. And in fact, this has much of the same look to it as what we had with a multinomial regression model. Now, if I had an ordinal response for my y, I could take advantage of that ordinal response by simply dropping the j subscript on each of those betas. And I could use that model to model my ordinal responses. Both of these models can be estimated using the VGLM function. That should be VGLM, that's actually a misspelling. And so if you're interested, you can take a look at the corresponding help for it. And I do have some exercises in my book that look at these particular kinds of models.